We had not earlier, we had not done this, and so I'm just going to cover it up. So please pay attention. The first thing you know to know about a spherical capacitor is basically when you hear the term capacitor, you should know that there are two conducting plates and they are in the form of a sphere. So let's say that there is a certain sphere here, there's another sphere here, and this makes it a spherical capacitor. That's it. Two conductors, okay, in sphere. So of course, one is going to have a certain radius. Let's say it's going to have a radius A. Another one is going to have a radius of B. Another one is going to have a radius of B. Now, when you connect this, okay, when you connect this to a battery, it is going to have some certain amount of charges discharged from the battery towards the capacitor, and the charges will be developed in such a way that this is plus, these are positive charges. And of course, I told you that if there is positive charge on one side of the conducting plate, when you bring another conducting plate next to it, it is going to attract all the negative charges towards it. So of course, by conservation of charge also we can say that this is going to be negative in nature. So definitely we are going to have a plus Q and a minus Q in the spherical conducting plates of a capacitor, spherical capacitor. Now let's consider the outer sphere to be grounded. Let me just say that I grounded this. If I have grounded this, of course, we know that the potential energy, okay, the potential at the outer layer of this conductor is basically going to be equal to 0. Okay, that is a fact. And also, let's consider a small point over here, right in the middle of this, having a some displacement dr, having some displacement dr. So there is a point I have taken right here. I hope you all can see, having some displacement of some certain distance, let's say it is dr. So right now, why are we doing this? We are basically trying to find out the capacitance of a spherical capacitor. So the first thing I told you in the general method is basically connect it to a battery, distribute the charges all over it. Okay. Then what you have to do after distributing the charges, the first thing I told you is to find out the electric field. So the electric field, okay, at any point outside a sphere is going to be what? At any point outside the sphere is going to be what? E is equal to kq by r square. Kq by r square. Why outside the sphere? And outside of which sphere? Let's say it is outside the sphere of this small sphere, outside. Why outside? Because basically inside a conductor there is not going to be any charge. No charges exist within a conductor, they are always on the surface. And so if we are trying to find out the electric field at a point we definitely need to find it outside the sphere. That is where the electric fields will be. Because also doing a small concept, I'll just let you know small concept which we had done previously, that the inside of a sphere, let it be solid or hollow, behaves like an equipotential surface. And by equipotential surface I mean that the change of potential is going to be 0. That means the potential at every point inside the sphere is going to be constant. So there is no electric field inside that. Okay, all the charges are basically outside, and we had also proved why they will be outside. Okay, why they will be outside. So coming back to this topic of finding capacitance of a spherical capacitor, the first thing I told you is to find out the electric field. And let's say that the electric field of what I've just found out is basically at the point which I've taken, having some certain displacement dr. If I know the electric field, the next step I need to know is find the potential difference, V. And what is going to be the potential difference is basically dV is equal to minus E dot dr. If I know this much, I can just substitute the value. So let's substitute the value. So dV is going to be equal to minus kq by r square into dr. Kq by r square into dr. But I want to know not the derivative of the potential. I want to know the potential itself. That will come with integration. So of course we are going to integrate both sides, and the integration of dV will be from, say, at a distance, at a point here initially, it might have a potential difference of, say, V minus going all the way to V plus. Okay, what I mean by V minus and V plus is basically the difference in potential. That's it. Okay, there's going to be some potential here and some potential at a further distance, at a distance of dr. So of course here the only variable is r. So we can integrate it with the limits of, say, a to b, some certain a to some certain distance b. I hope this is clear. If we solve this integration, what we are going to get? What we are going to get? Let's say, let's 1 minute. This is v plus and this is v minus. Okay, because of course the potential is going to drop from a point initially to a further point. Potential is going to drop, so v plus to v minus. So let's integrate it. So what we are going to get? We are going to get v minus minus of v plus equals to, okay, v plus is this one, v minus is this one, is equal to minus of kq upon r, kq integration of r square from the limit a to b, 1 upon r square dr. The integration of 1 upon r square is what? Minus 1 by r. So if I directly resubstitute it over here itself, I am going to get minus 1 by r a to b. And if you can write that again, that will give you, okay, it's going to give you minus kq. Of course, this will become plus if I take the minus outside, and it is going to be 1 upon b minus of 1 upon a. 1 upon b minus 1 upon a. Now, if you take the LCM of that, what you're going to get? You're going to get that v minus minus of v plus was basically equal to kq ab, and it will be a minus b. If I change the order of this as v plus minus of v minus, in that case even the signs over here will change. So we can change the arrangement to b minus a upon ab, b minus a upon ab. Now what we can say, since I am looking at a capacitor, I want everything to be in terms of capacitance. I can say that v plus minus of v minus is basically what? Potential. V kq b minus a upon ab. I can say that. And now we also know the relationship between charge and potential, which is basically capacitance. So q is equal to cv. Q is equal to cv. So I can say that c is equal to what? C is equal to q by v. Of course you can see here q, of course you can see here v. Just take v there and rearrange the terms. You're going to get, okay, what will you get? Q by v is equal to ab upon k b minus a, and q by v can be written as c. So I will write c is equal to a b upon k b minus a. C is equal to a b upon k b minus a. I will write that on top for you. So you'll get the idea. So we got that C is basically equal to, okay, what we got? We got it as KAB upon B minus A. This is what we got. But K is also 1 upon 4 pi epsilon naught. So I will write that C is equal to AB upon 4 pi epsilon naught B minus A. 4 pi epsilon naught B minus A. So this is finally the capacitance. This is finally the capacitance of a spherical capacitor. So what I did first was basically I found out the electric field at a point outside the sphere, and that was E is equal to KQ upon R square. After that, I found out the potential, that is basically, what did I do? I found out dV is equal to minus EDR. Integrated it from a certain potential V plus to a certain potential V minus. V plus is basically the potential energy at a point near the plate, which is having the plus charge, and V minus is basically the potential drop, of course. As you go further away, the potential is going to drop, and that is why V minus. Then we found out the potential difference, and after potential difference was found out, we said that Q is equal to CV. Basically, we now know the charge Q, and we now know the potential difference, so we can find out the capacitance. So the steps to always find out capacitance is basically to first take the capacitor in whatever shape it is, connect them to a battery. Once you connected it to a battery, distribute the charges all over the plates. Distribute the charge all over the plates. Find out the electric field at a point in between those plates. Later on, what you have to do is find out the potential energy. After finding out the potential, you can find out the capacitance. These are some 3 steps to find out the capacitance of any particular shape. Let's talk about cylindrical capacitor. So in cylindrical capacitor, basically the plates will be 3-dimensional in nature, and they will be cylindrical in nature. So I can draw 2 plates, an inner plate in this way and an outer plate like this. Okay, an outer plate like this. So this is a cylindrical capacitor. We can of course do the basic things that need to be signified over here. That will be the radius. Let's say that is R1, and let's say this entire radius is going to be R2. Okay, once we know that, we also can see that the entire length can be taken as L. Okay, entire length can be taken as L. Now, in order to find out the capacitance, the first thing that you need to do is to find out the electric field. Once you find out the electric field, you can find out the potential difference. Once you find out the potential difference, you can find out the capacitance. 3 basic steps. The first thing you need to do is first connect this entire capacitor to a battery. When you connect it to a battery, the battery is going to supply some amount of charge in the form of plus Q from the positive terminal and minus Q from the negative terminal. When it reaches this capacitor, the plates are going to develop charges across it. Let's say this is going to be plus Q right here and another one minus Q here. Now, in order to find out the electric field, okay, we can use our method we had done previously. We can take a Gaussian surface. So let's take a Gaussian surface here, which also will be in the form of a cylinder. Okay, also in the form of a cylinder. Wait, I'll write this R2 somewhere else. Okay, this is a Gaussian cylinder. I will write the R2 right over here. And let's say this Gaussian cylinder has some radius r. Let's say it has a radius smaller. Now, you need to keep in mind that R1 is basically the radius of the inner cylinder. R2 is the radius. I'll write this in black so that it identifies with the color. R2 is the radius of the outer cylinder. Small r is going to be the radius of the Gaussian surface. Now let's write the formula for Gauss's law, and that is total flux phi is going to be equal to charge enclosed upon epsilon naught. But phi can be written as E dot dA equal to charge enclosed upon epsilon naught. And of course, this is going to be an integration based on surface integral. Once we know this charge enclosed by this Gaussian surface can be written in terms of surface charge density. Okay, so I can say that lambda is going to be what? Q upon L. Can I write that? Q upon L. I will write it down. And then I can say that Q is going to be equal to lambda times L. dq is going to be equal to lambda times dl. dq is going to be equal to lambda times dl. But this charge density which I'm talking, of course, is the charge enclosed. By charge enclosed by what? Gaussian surface. And the length of the Gaussian surface, I have not specified that. Let's take that as x. Let's take it down as x. I've written that x over there. So instead of dl, I can write lambda times dx, because I'm talking about the Gaussian surface. Now, once we know that dq is equal to lambda times dx, I can know what q is. Q will be basically integration of both these terms. And so what I will get is q is equal to lambda times integration of dx, that will be x. So I know that q is equal to lambda times x. And lambda is basically the surface charge density of the entire cylinder. And which cylinder am I talking about? The inner one. So the inner one is going to have a total charge capital Q upon length L, that is lambda, Q by capital L into X. It's just this. I've taken lambda and I've written lambda as lambda is going to be equal to the surface charge density of the entire capacitor plate, which I'm talking about the inner one. I'm talking about the inner one. It is going to be capital Q upon L into X. So I can take this and I can resubstitute this value in the main formula. Let us do that. Now, what you can see here is that dA is basically what? dA is the area of the Gaussian surface. And the area of the Gaussian surface is going to be what? E dot 2 pi small r, because r is a small radius of the Gaussian surface, into the length x, equal to integration of Q by L times x upon epsilon naught. Of course, you can see that x and x get cancelled here. Okay, x and x will get cancelled here. So ultimately, what you are going to get is E 2 pi r equal to Q by L upon epsilon naught. And I can take 2 pi r over there. If I take 2 pi r over there, I will get E is equal to Q by 2 pi small r L epsilon naught. This is the electric field. This is going to be the electric field. Once I know the electric field, once I know this electric field, I can start to find out the potential, because that is the third step. First, distribute the charge. Second step, find out electric field. Third, find out potential. And potential, we know the formula that dV by dr, okay, minus of dV by dr is going to be equal to E, or dV is equal to minus E dr. If you resubstitute that formula, you're going to get, considering the fact that you are taking a point, okay, somewhere over here. Again, I can say that the potential is going to be from V plus to some potential drop V minus dV, which is going to be equal to minus upon Q 2 pi r L epsilon naught dr, where E is equal to this value, and I've resubstituted that value. If I do that, then I'm going to get V minus of V plus equal to minus Q upon, this is the integration over here, 2 pi r L epsilon naught r from, let's say, r is from r1 to r2, a point I'm taking right here, which is going to travel from r1 to r2. So I can take the limits from r1 to r2, and that will give you what? That will give me, first of all, integrate dr. Sorry, I have to take this r inside. So integration of 1 upon r will give you what? Integration of 1 upon r will give you log r. It will give me log r. So I can write log r with the limits of r1 to r2. With the limits of r1 to r2. So I can write that v minus of v plus is going to give me minus q upon 2 pi r L epsilon naught log of r2 minus r log of r1, and that is going to give me log of r2 by r1, log of r2 by r1, and log of r2 by r1. Yes, so potential difference v minus v plus is equal to minus q upon 2 pi r L epsilon naught log of r2 by r1. But we can also see here that this can be rearranged as v plus minus v minus. So I will do exactly that. Just writing the terms above, that is going to be, going to flip the sign, v plus minus of v minus. If I flip the sign, then of course this sign, that is minus, will also move out, so it will become q upon 2 pi r L epsilon naught. Sorry, this r does not exist. 2 pi, because I had integrated that r, that is my mistake. So 2 pi L epsilon naught log of r2 upon r1, log of r2 upon r1. But if we know that v plus minus of v minus is basically the potential, I can write v is equal to q upon 2 pi, I'm taking it as v, L epsilon naught log of r2 by r1. Now, if this is my potential, then finally I can look here. I know that q is equal to cv, and I can say that c is equal to q by v. Can you see q and v over here? So can we rearrange these two terms as q by v? And if we are able to do that successfully, basically we found out what capacitance is. So I will do that. So what am I going to get? Q by V is going to be equal to 2 pi L epsilon naught upon log of R2 by R1. And this is going to be equal to C, Q by V. So C is going to be equal to finally 2 pi epsilon naught L upon log of R2 by R1. This is the capacitance of a cylindrical capacitor. This is the capacitance of a cylindrical capacitor. Try this yourselves so you get an idea of how to solve sums like these. So, a concept about Wheatstone bridge. Earlier we had done problems in this format. And when we had done this problems in this format, what I basically told you was, if in order to find out the equivalent capacitance, you have to connect it across a battery. And if we connect it across a battery, it is going to develop certain charge plus Q from the battery and minus Q from the battery. Of course, due to the symmetry, I can say that the charges are going to split in they're going to split equally. So I can say it is Q by 2 here, and I can say it is minus Q by 2 here. Sorry, plus Q by 2 here. Both are going to split. Q is going to split as Q by 2 and Q by 2. Ultimately, these capacitors will develop a plus Q by 2 on this left side of the plate, and opposite plate will get minus Q by 2. Similarly, plus Q by 2 over here, minus Q by 2 over here. And over here, it is going to be minus Q by 2. It's going to be plus Q by 2. This is going to be minus Q by 2. It's going to be plus Q by 2. And let's say that the capacitors are arranged as C1, C2, okay, C3, C4. Now, if I take, I have already done this earlier, but just to make you all understand, if I take a surface like this around the conductor, I can say that by conservation of charge, if there is a plus Q by 2 and minus Q by 2, if I have to find out the charge developed on this plate, I can tell that it is going to be equal to 0. Because we all know that conservation of charge is basically meaning that the net charge should be equal and opposite. And you can see here that we already have a plus Q by 2 and minus Q by 2. So there won't be any charge developed on this capacitor. And similarly, it's the same concept over here in this surface as well. It's going to be 0 on this side also. So what I'm saying is basically that there will be absolutely no charge flowing through that capacitor right in between. And if there is no charge flowing through that, we can ignore that. So when it comes to cases like this, I can develop a ratio for the symmetry. I can develop a ratio for the symmetry. A certain observation. The observation is that in terms of symmetry, if my C1 upon C3 is going to be equal to C2 upon C4, that is this capacitor here and these two capacitors here, If their ratio is going to be equal, then I can forget the one in the between. I can take the ratio sideways as well. I can say C1 by C2 is equal to C3 by C4. I can even take the ratio cross multiplying it. That is C1 C4 equals to C2 C3. If these ratios are fulfilled, then you can definitely neglect the capacitor in between. This is the concept of Wheatstone bridge. I'm urging you all to please try all the problems of capacitors. Okay, you all might understand the concept here, but you all need to solve the problems. There has to be a certain practice. That is when it will be easy for you all. Also, the same things will be covered in current electricity as well. If you understand it here, it will help you there. Let's talk about the work done by the battery. Now, what is the work done by the battery? In the lecture we had during the morning hours, we found out the work done between a capacitor, between the plates of a capacitor. But now we'll try to find out the work done okay, by the battery. And so in order to do that, we can take two plates of a capacitor, that parallel plates again, of course. Once you do that, we can connect them to a battery. When you connect a capacitor to the battery, by now you must be knowing by heart. It is going to develop a plus Q over here, a minus Q over here. And so ultimately you're going to get a plus Q over here and a minus Q over here. The charges will be in this form. Now, when we talk about the work done by a battery, we can say that the work done externally is going to be equal to what? Work done externally is going to be equal to delta U, change in potential energy. We have done this formula that du is going to be equal to dw external, which is going to be equal to minus dw electrostatic. And the work done by the external is of course opposite to the work done by the electrostatic work or electrostatic force. So I am writing from this relation that work done externally by the battery is going to be equal to delta U du, or rate of change of potential. And we also know that the potential delta V is going to be equal to delta U by Q. We know this, we have done this for point charges where we try to find out the potential due to 2-point charges when they are close to each other. Delta U by Q will give me the potential. And so from this I can rearrange the terms and write delta U is equal to what? Just write that as U. Is going to be equal to delta V times Q. So now I want you all to remember this thing, because this is going to be used many times further. Okay, I will write this relation again. You all can write it in your books that du is going to be equal to minus dw electrostatic plus dw external, and it's also going to be equal to delta V times Q. Delta V times Q. Du, this delta V times Q we have found out from here. Of course, this is delta U. So du equal to minus dw external equal to dw, minus dw electrostatic equal to dw external equal to delta VQ. Please remember this relationship. You can jump from, you can be given this, you can be asked this, you can be given this, you can be asked this, anyhow. So once we know this relation that delta U is equal to delta V times Q, can we substitute it over here? So let's do exactly that. So I will write that delta U is equal to delta V times Q. So I will write W external is going to be equal to delta V times Q. So this is, let's say, our first point, and this is going to be a second equation. Now, if you see from here, the first and the third equation simply say that the work done by the external force is basically the change of potential energy. The change of potential energy is delta V times Q. And of course, the work done externally is basically the work done by the battery. So instead of writing work done externally, I can write work done by the battery. And that work done by the battery is basically capital Q times V. I'm taking the entire charge to be Q. This Q, small amount of charge, I'm taking it as capital Q, and the rate of change of potential as V. So the work done by the battery is Q times V. Please remember this. Work done by the battery is Q times V. I'm going to further derive another expression, and we will have to use this. And so remember that work done by the battery is Q times V. Let's now try to find out that if the work done by this battery is Q times V, by distributing these charges Q and minus Q, let me just see whether that same amount of energy has been transferred here or not. Okay, simple as that. There is some work which is done by the battery, it is equal to Q times V. I want to find out the energy in this capacitor, and I want to find out whether that is equal to the work done by the battery or not. That is all my intention is. So in order to do that, I know that Q is equal to C times V. Q is equal to C times V. So I will substitute Q in C times V over there. We don't mind because the expression is going to be a little bit long. So I know that the work done by battery is going to be equal to Q times V, and Q is equal to CV. So I will write CV into V, that is CV square. And I can play with this by writing, if Q is equal to CV, then V is equal to Q by C. And so if I substitute that over here, it is going to be C Q by C whole square. And you're going to get Q square by C. So this is work done by the battery in terms of charge and capacitance C. In terms of charge and capacitance C. I can say work done by the battery QV can be written as Q square upon C. Now the potential energy between the capacitor plates was how much? Earlier we had done this. We had tried to find out the potential between the two plates, and we found out to be half CV square. We found out that U is equal to 1 by 2 CV square. Okay. Today morning itself we had done 1 by 2 CV square, which is also equal to Q square by 2 say, which is also equal to 1 by 2 QV. These were three formulas which we had done. So if you see, work done by the battery will be having some potential, will be basically potential only, because du is equal to what? WB or W external, which is WB here. So the work done by the battery is Q square by C, but the potential energy stored by this capacitor is Q square upon 2C. That means the potential energy or the energy stored by the capacitor is only 1 by 2 times the work done by the battery. So I can write here that the work done, the potential U is basically 1 by 2 times the work done by the battery. So in that case, I want to know where the other half of it has gone, because the work done by the battery is q square by c. It is a whole term. Potential energy is basically half times the work done by the battery, and potential energy is the energy stored by the capacitor here that I'm talking about. So if U is equal to 1 by 2 times the work done by the battery, I want to know where the other half of this work done by the battery is gone. And that work done, okay, that work done which is lost, or that potential which is lost, okay, that potential that is lost is basically lost in heat. It is lost in the form of heat. So I can say that the heat has basically consumed the other half of q square by c. I can say that the heat has consumed the other half of the work done by the battery. I hope this is clear. I hope this is clear. So ultimately, heat over here and the potential energy that is stored by this capacitor are both one by two. You can see here. You can see here that even the heat is lost as 1 by 2 q square by c, and even the potential energy that is stored by the capacitor is 1 by 2 q square c. So both are equal in magnitude. So I can of course say that since they are equal in magnitude, heat is going to be equal to 1 by 2 cv square. Okay, I'll tell you from where this term has come. Q square by 2c, and is also equal to 1 by 2 qv. Basically, this is also equal to the potential energy between the two plates. That is also 1 by 2 cv square, q square by 2c, and 1 by 2 qv. And the work done by the battery is q times v. So the work done by the battery is exactly split into two. It's split into two halves. One is stored as potential and one is stored as heat. One is lost as heat. See, these facts are actually very interesting. The reason is when you now look at a battery and now when you look at a circuit, you can immediately look at it with a different perspective. Don't just look at it as terms of studying. Just see, just try to imagine how we came up with all of this. It is just extraordinary to find out these things. It's a wonderful thing. The more you appreciate these things, the more you learn physics. That is the only way I can say. The more you appreciate things like this, the more you will be able to change your perspective in terms of knowledge and also appreciate small things in physics. So this was the work done by the battery.